shear force and bending moment diagram for the beam below. Just take two more examples from the beam for the beam below. Let's see here. So observe please, think away the whole support something. I went straight to free body diagram, right? Yes. So let's just save time. If they give you a normal beam, you know what is that beam? Just change and put this. So draw the shear force and bending moment diagram of the beam below. This one here. Of the beam below. This one here. Of course, you don't come and say, draw free body diagram. It's already a free body diagram, right? So, go straight to solving. Your task now be reproduce diagram and go straight to solving. Can we start? Yes. Alright, are we good? Yes. Finish and so you look up and observe. The concept here will now change again. Will now change again. Are we done? Yes. So look up. My first task, of course, is that what there? Summation of vertical forces equal to 0. So I'm saying sigma summation Fy vertical force equal to 0. Going upwards to be positive. So look at this page. How many forces do we have? 4. 1, 2, 3, and 4. It's going upward, positive. When it's going upwards, it becomes positive ROA. Next up, this is coming downward there, but it's a UDL. So convert to point to, it becomes what there? Multiply the UDL by what? UDL distance. Look up, look up, look up. Multiply this UDL by distance, it becomes what there? 3 times how many there? Please observe, for this one, distance is 2. So 20 times 2, I have this. This one, 2, is coming downwards, becomes negative. Convert this UDL to point low. Multiply this UDL by the distance it's covering. So it becomes what there? 40 times 4. Next up, here's a point low going upwards, plus RB. Equal to what there? 0. Work this out. ROA minus 40 minus 160 plus RB equal to 0. Hang on. Look at this diagram, please. Which do you think will have a greater magnitude? ROA, RB? You're saying that RB should be greater than ROA. Okay, let's confirm that. From here, means that ROA minus 40 minus 160 minus 200 plus 1 there. RB equal to 0. Move this one over here. I have that ROA plus RB equal to 200 kilonewton. That's my first equation. Let's now take moment. So depends, what think about A or B, whichever one. Choosing D. Taking moment about B. What do you have? That the sum of the moment about B should be equal to 0. And of course, take the clockwise direction as positive. Please stop writing and focus on this. See the change here. Let's think about B. That's this point. So that means all the forces are coming to this point. So it means that all the forces are coming to B. And of course, this force at B will not be included. Okay. That means I work with just 1, 2, 3. Now see the technique of taking moments now for this case. First of all, this one is coming this way. That this is the motion. As it clockwise, it becomes RA times distance from here to here is 6 meters. That's 6. I'm done with this. Next up, this one here is coming downwards like this. Downwards like this. So it becomes negative. It's anti-clockwise. Convert this to a point load. How do you do that there? Multiply the UDL 20 by the UDL distance. How many there? 2. This is the force. Now get distance. What distance is it? What distance? Hold on, see. So this becomes half of total length. That becomes half of the UDL length. That's 2. Now observe, half of 2. It means it starts from here to this point. That's the concept. Half of 2 means from here and the center from here to this point. But think about this point here, not this one. So it becomes half of 2, that's from here to this point, plus this one again. So plus what again there? 4. And that's the 5 I was saying. See the concept now, that's shown again. Moment at this point there, it said becomes half of UDL length. Half of this will be from here to this point, it ends here. But I said moment at this point, so add up this as 2, becomes plus 4 there. I'm done with this one here. Pick up this one. This one is going downwards to this point. Down like this. Anti-clockwise. Negative. Convert UDL to point load. Becomes 40 times. This one is covering just distance here. Times 4. Here's my force. Now get distance. Distance becomes half of 4. Look at this. If here is 4, half of 4 becomes from here to this point. True of course? Am I adding an extra length? So I'm not adding, stop there. So this is equal to. So see the difference between the two. For this one, if you take half of the length to be from here to here, you have to add this distance so it gets here, plus 4. For this one, by the time you take half for this one, it becomes half from here to this end. It's now at this point. I'm not adding extra length. That's the concept. Any questions? Let's repeat it. Okay, just hang on. Let's finish this. My recording session. Let me finish up first.
What if we learn before?
Relax, let me finish up first. My recording session. Right. This gives you what here? 6 RA minus 40 into half of 2. 1 plus 4. Please do and do both math. So it's not 2 plus 4, 6. Half of 6, 3. Come on, it's in 3. Minus 40 times 4, 160 into half of 4, 2 equals 0. So I'm having 6 RA minus this 200, okay, minus this 320 equal to 0. 6 RA minus 520 equal to 0. 6 RA is equal to 520. How do you get RA? Divided by 6. Divided by 6. This cancels this. So RA is equal to what value? Sorry? 86.67 kilonewton. So put the value of RA into 1. So put RA into equation 1. From 1 here, I have RA, whose value is this? 86.67. RA plus RB is equal to this one here, 200. Bring this man here. I have that RB is equal to 200 minus 86.67. Now you see what there? 13?
No, 113.
113.33 kilonewton. That's RB. So yeah, it's true that RB is bigger than RB. And hey, so explain what the game is.
So what if 4 is not what if you learn?
You don't add this 4. It's wrong now.
That's 4 for the
If you don't add this 4,
yes.
it's wrong now. Now listen. Please, when it comes to learning engineering, you keep an open mind. What's open mind there? It must not be this way. The concept will always change depending on what they're being given. If I'm giving a UVL now, this whole thing will change. For this I'm even using time. For UVL it becomes 3/3 of the length and 2/3 of the length. That's UVL concept. And I'll tell you why it's so. Right, so when it comes to just keep an open mind, it must not be the way I saw the first one, must not be similar to the second one. But get the concept. And take a note about this one. What do I do? It's simply this one coming here. So this times distance, that's all. For this one is UDL, convert to point load. Because this 20 times the distance of this UDL, not times 6. It starts here and ends here, that's 2. 20 times 2, that's the force. Distance is at this point. Half of the UVL length is from here. Half is from here to here. And think about this one, not here. So it becomes half to this one plus this length here. So plus 4. That's the concept. This one too is anti-clockwise, negative. Convert it to point load. 40 times distance. 40 times 4. At this point is a force. What is distance there? Half of the length. Half of length is from half of this to this one. It's now this form. That's it. Should we take a moment about it? Yes. I see the same thing.
Yes, the same thing.
Okay, look at it.
Yes, sir.
You've done it. Or should we do it?
We should do it. Yes, sir.
Now look up. Look at your own. Look up. Look up now. Look up. Moment about E. What will it be there? This will be clockwise. Abi? This becomes what there? Clockwise. Clockwise. This becomes what there? Anti-clockwise. So what will this be? 20 times 2. Abi? Yes. Then times what again there? Half of 2. Will I add that length here? No, not add length. It's not this word there. For this word here, how do you solve this? 40 times 4. That's the force. Yes. Distance becomes what there? Half of this length from here to here. Will I add the length there? Yes. Plus what again there? 2 plus 2. That's it. Then minus RB times what there? 6. You do it, you have the same answer. Alright, shear force calculation. Shear force. You don't need to know. Huh? Shear force. Please, for this case, please. For this case, please. Where do I take interval?
Yeah. As two.
Whatever you read this line, always take intervals at the start and the end. I don't want to at x equal to. How do you skip here? Start from here too. Whichever point you want to take, you must start from the beginning and also get the end. You must include them. So what will you be there? 0, 2, and 1. Okay? 1, 2. If you think you have time, you're fast in writing. Do 0, 1, 2, 3, 4, 5, 6. Well done, eh? Well done. So first of all, at x equals 0, that's my starting point. At this point here, now remember it's shear force. It's shear force. It's going up positive. RA is going upwards. Becomes positive. So shear force is equal to RA positive. That gives you what there? What's RA? 86.67 kilonewton. I'm done. Next up, they said it's at x equal to 2. At x equal to 2 meters. Please, at 2 meters. Now listen. Question. If I choose to take at 2 and 6 only, is it correct? I say I want to skip this point here. Is it correct? Yes or no? No. Remember the taking point. It said you take at 2, at 0, at 2, and 6. No problem. Now I'm now proposing something. What if I don't have time? And I say I want to take at just 0 and 6. Would that be correct? Yes. Yeah. Why? Because there's no point loads. Please. The most important thing there is point load, not UDL. So I made that emphasis. I said you must take intervals at where I have point load. What about UDL? It doesn't matter. Doesn't matter. Why? I will show you some shortcuts. So if I choose to say 0, look up. If I choose to say 0 and this, I'm good. But after I will show you shortcut. So at x equal to 2, let me just do 2 for doing sake, right? At x equal to 2, here's my point. So before this point, please check. How many forces is there? 2. This and this. This one is going upwards. That's RA. UDL is coming downwards. Becomes minus. Convert UDL to point load. Becomes what there? 20 times 2. Becomes minus 20 times 2. RA is 86.67 minus 40. That gives you what there? 26.67. Was that correct?
46.67.
46.67. Alright. Of course, there's no condition. Abi? Why? No point two. Next up, please. At x equal to 1 meter, 6 meters. There will be two conditions, Abi? Yes. Yep. 6 is here. 2 and 4 is 6. So at this point here, you can see a point in here, RB. So two conditions. Two conditions. Condition 1, shear force is equal to all the forces before that point. Look at it. Before this point, what do I have? I have this. I have this coming down. I have this coming down. So it gives you RB this one coming down, convert to point load, minus 20 times 2. Next up, this one also coming down, convert to point load, minus 40 times 4. Alright. Alright. Condition 2, okay, finish one up here. So it's equal to RA is 86.67 minus 20 times 2 is 40 minus 1 times 4 is 160. Please give me value. Minus 11.331 there. You don't need to. Alright. Condition 2. Shear force is equal to all the forces for that point plus the one at that point, which is simply a repetition of condition 1. That's RA minus 20 times 2 minus 40 times 4. Then plus, at this point, I have RB is going up to because of that, plus RB is equal to 86.67 minus 40 minus 160 plus RB in value is 133.1, right? 113.33. This is not give you, all of this will give you minus 113.33 plus 113.33. This is what we want, right? Shear force always end to 0. Next up, bending moment calculation. Of course, first up, at x equal to 0, my bend moment is what there? 0. Next up, at x equal to 2 meters. Look at this. At 2 meters, look at this. At 2 meters, here's my point. So get bending moment at this point. Of course, I will have that bending moment is equal to, at 2 meters, here's your point. So look at this place. So become this one times distance, that's RB times 2. Next up, convert this to point to 20 times 2. That becomes anti-clockwise minus 20 times 2. Then what again there? Half of the distance. Observe, at 2 meters, here's the point. If I take half of distance, become from here to this point. That means I don't have to add an extra length, so stop there. So I'm having this. Do you understand? So it's now equal to RA 86.67 times 2 minus 40 times 1. That gives you 463 173.34 minus 40. This mean value 133.34 kilonewton meter. Finally, at x equal to what there? 5 meters. 6 meters. X equal to 6 meters. My bend, please can you bend my please at x equal to 6 please. Hold on. I got this chop which is finished already. They were almost like 2 pack of chop in a week. Like full pack, 2 in a week. 2 to 3. What do I mean? Give me at x equal to 6 there. Give me the value. What do you have there? RA times what? 6 minus 20 times 2 into what there? 1 over 2 times what there? 2. Am I adding? Yes. Plus what there? 4. I'm having this. Is that all? Minus 40 times how many there? 4. Is that all? No. What again times how many? Am I adding? No. Alright. This now gives you 86.67 times 6 minus 40 into 5 minus 160 into 2. This value is 5202 minus 200 minus what there? 320. This now gives you 520.02 minus 520. Is it what there? The other point was, which is approximately what there? So I said when you're doing shear force and bend moment diagram, bend moment will start with 0 and give you 0. In case where you have this kind of stuff, it happens when my reactions are in this amount. Give you something close to 0. So it's 0, approximately 0. That's it. What do what? For what? We're doing bending moment, not shear force. Now listen. So ask a question. Someone said, in this point here, I need 2 conditions. Why? The point low. But in this case, I did not do 2 conditions. Why? You see, a point low here. So why no 2 conditions here? Huh? Because it's 2 conditions. Condition 1, all the forces before that point. Before this point, this is the start of the beam. Before here, is any force before here? Just go to this step, condition 2. Let's draw shear force here. Let's draw bending moment. Next, let's look at other concepts. So, shear force and bending moment diagram here. RG is equal to 86.67. RG is equal to 113.33. Of course, in kilonewton. Of course, in kilonewton. Alright. So here's 20 kilonewton per meter, like this. Here is 40 kilonewton per meter. From here to here is 2 meters. Here to here is 4. That's 4 meters. Give you 6 total left. Alright, so bring down short dashes at points where you took intervals. That becomes short dash here. Here 2. Short dash. Here 2. Short dash. Alright. Bend moment, any negative value? No. My datum will now be here. That's bending moment. Okay. Shear force. Somewhere here. Alright, so at this, I had about 6.67. Let me assume this point here is 86.67 kilonewton. At x equal to 2 meters, what was your distance? What was your shear force value?
6.67.
Huh?
46.67.
Okay, come around here. 46, hold on. 46.67 kilonewton. At x equal to this point, there are two conditions. What are what?
Minus 100.33.
Minus 100.33. So let's call this point here as 100.
113.
Huh? 113.
Yes.
113.33 kilonewton, and then 0. I think I people know this, right? This from here, trace this point, join them, we'll have here was 46.67. 40 what? 46.67 kilonewton. So then above this should be positive. Here. Below this should be negative. This. Let's now get bend moment. Now look at this. Without stressing myself, I said the bend moment will occur at one point here. Maximum will occur here. The maximum bend moment will occur where shape was what there? 0. So no matter how you want to curve it, right, at this point, here should be your maximum. So I will draw something like this. Something of this nature. At this point here, where is 0? Go back, do that. Comes this. Please, at this point, what was your, sorry, at this point to 2. What's the bend moment value? 133.34. 133.34 kilonewton. That was at this point here. Equal to 2. But the maximum will always be at where shear force is here. Of course, above that. So positive. This. Alright, so that's your shear force bending moment diagram. Alright, so ladies and gentlemen, you can follow the Abby? Yes. Let me show you before you go.